Hello, everybody. I hope all of you are doing great today. If you're not at your best, I promise you, better days are coming. Now, I know this topic may be a little bit of challenge to most persons in writing the equations and predicting possible atoms that may form. So what I'm going to do today is to kind of dummy down this topic so we'll be a little bit more confident going exams and writing answers for particular questions. So I want to bear with me while I go through this in small chunks to make it more understandable. So the first thing I want to do is to go through a concept with you, right? And what I want you to understand is that unstable atoms will release radioactive substances or radioactive particles. In some instances, the atoms may also absorb radioactive particles. So there are two scenarios: either absorbing radioactive particles to become more stable, or releasing radioactive particles to become more stable. But the idea is that the nucleus of an atom will either absorb or release these radioactive particles. And that is why we can call this type of reaction nuclear reaction, because the reaction is taking place inside of the nucleus. All right. So what I want to do next is to really jump into the type of particles, their symbols, their charge, and also their mass. Now, first and foremost, let's deal with alpha particle. Alpha particles resemble helium particles, or the nucleus of an helium. The next part we're going to talk about will be beta particle. So the beta particle, they are fast moving electrons. So their properties are just like electrons. And then we have our gamma particles, which are electromagnetic in nature. Now, I'm going to show you something right here, right? Because we said that the alpha particle is just like the helium nucleus. Now, remember that inside the nucleus of an atom, there are two important subatomic particles. These subatomic particles are protons and neutrons. The sum of protons and neutrons result in the mass of the atom. However, today we're going to only deal with the mass number and the proton number. All right, those are the two particles that we are concerned about. Once we talk about radioactivity, radioactive reactions, we're only concerned about the mass number and the number of protons. All right, so first let's look at the symbol for the alpha particle. The alpha particle, again, remember, it resembles helium. So the mass number for helium is 4. The proton number is 2. You can substitute this symbol with He, because remember, alpha is also resembling helium. A matter of fact, in this lesson, I'm going to use helium particles, right? The He symbol for the alpha particle. Now for beta, the symbol here, again, remember, you notice the 0. And the 0 is because we said that beta is an electron. Electrons theoretically have no mass, right? So the mass is taken to be 0 because the mass is so small compared to the proton and the neutron mass. Now, an electron is technically, if you think about it, it's a negative proton, right? It's a negative charge. That's an electron. And that's why the proton number is a -1. I'm going to show you an application for this later on, but I'm going to tell you this right now, is that if you lose electrons, you technically gain protons. Because a loss of electrons, you gain a positive charge. So I want to kind of have that in your mind, right? Losing negative things, you gain more positive things. So loss of negative character, you gain positive character. So I want to have that in your mind, right? So when I go through it, you're going to see how this is applicable. Now, the gamma particle, now, it is electromagnetic. So there is no charge on gamma particles. Neither there is any mass. Because simply put, gamma particles are just energy in motion. All right? So now the charge on the alpha particle, we can easily determine that, because if the alpha particle has 2 protons, the charge have to be positive. Let's look at the beta. The beta is an electron. By nature of being an electron, we know that must be negative. A negative charge. Gamma straight off the bat, no charge, as we mentioned, right? Now the mass number for these now, again, another concept to look at is, remember, alpha represents an helium nucleus. And a helium has a mass of 4, so we know that the mass number or the mass for helium or alpha particle is 4. Now, even based on the symbol here, electrons, again, I said theoretically there is no mass. So this is going to be 0, right? Gamma, no mass as well, so that's going to be 0. Now, so based on these values in examination, some typical questions they may ask you is, which of the radioactive particles will contribute to the greatest loss in mass? That will be an alpha particle. They can also ask, which of the radioactive particles will contribute to the greatest change in proton? And that is also alpha particle, because alpha has the greatest mass and the greatest what? Proton. So therefore, alpha particles will result in a greatest change in mass and also proton compared to the other radioactive particles. In fact, the beta and the gamma, there's no mass, so they do not affect the mass of an atom. All right? So, of course, beta and gamma will be the particles that least affect the mass of an atom. All right? Just bear that in mind. All right, I'm going to jump away from this a little bit. All right? We'll come back to this later when we're doing our reactions. But by nature of these charges, I want to look at something. So we're going to understand the nature or the properties of these particles a little bit more, right? So what I want to look at here, let's say you have a source that is producing radioactive particles. There are 2 charge plates. So these plates are charged and there's a screen. If you should shoot some radioactive particles between the charged plates, you notice there are certain behavior with these particles. By virtue of the alpha particle being positively charged, it will deflect towards the negative plate. The beta particles, they are negatively charged, so they will deflect towards the positive plate. Because remember, opposite charges do attract. The gamma particles, they will remain unaffected. There is no deflection, there is no change, because they are neutrally charged and hence they will pass straight through. So there is no deflection with the gamma particles. All right, I know you're excited to get to the reaction part of it, which I soon get to. But at least I want to just cover these basic concepts first before I jump into it. So next concept I want to look at here before I go into the reaction part of it, which I know you're truly excited to. I'm also excited to reach the reaction part as well. But let's just jump into this little piece right here, right? So if these particles are released, they are energy in themselves, right? Remember, they contain energy. They are energy in motion. And so if there's nothing shielding these particles, by law of movement, they will continue to move. However, now, if you want to shield these particles because they're dangerous and you use a sheet of paper, the sheet of paper will only stop the alpha particles. The beta and the gamma will go straight through the paper. So paper cannot stop beta and gamma particles. However, now, if you apply an aluminum or a thin piece of lead, the beta particle can be stopped. The gamma will go straight through aluminum and thin lead. So how do we stop this gamma particle? The way we could stop it, if we use like concrete or thick lead, then we could stop it. And of course, you have to know these properties because remember now, radioactive particles can be dangerous. And so you have to know how to shield them in certain applicable situations, right? So you have to also know those. So the easiest particle to be stopped is alpha, then beta, then gamma. So gamma, of course, by nature of this, will be the most dangerous because the shielding effect of it is higher, right? It requires a greater shield or a thicker shield to prevent it from passing through objects and so on. All right. So what I want to look at now are some common terms that are normally used in radioactivity questions. And I want you to be familiar with these terms. And so typically, remember in the first diagram that I shown, I said that the radioactive particles can either release from the nucleus or absorbed in the nucleus. So in the questions, what you may see that relating to releasing of radioactive particles, you may see the word emit, lost or remove, decay, or given off. So those are things that you want to focus on, right? And make sure you kind of look out for these terms because sometimes there's a wording of the question that may play a trick on your mind, and I want to kind of look out for those things. Now, when you talk about absorbed, they may use the word bombarded, gained, added, collide, and even capture. So look out for those terminologies. All right. So once you understand this now, we can pretty much jump into some questions. Oh wow, why am I showing a burger and we're talking about radioactive substances? That must be a mistake. Actually not, I'm just kidding. I really want to show the burger, not because I wanted to feel a little bit more hungry than you are right now, or cause it to drool while studying. But I want to use this that we can relate to understand the concept of the equations, right? So I'm going to use the burger. And remember, we're talking about decaying of unstable nuclei. So if an atom has an unstable nucleus, it will either release the radioactive particle or absorb it and become more stable. So that's the idea. So let's say I have a burger and I want to break down the burger. I want to decay the burger, right? Let's use the word decay, not as in spoilage, but to break down, right? I want to break down this burger. Maybe because I don't like lettuce, or maybe I don't like the meat for whatever reason, right? And so if I want to break this down, what I might get the bread or the bun, you may want to call it, with the meat inside, whether it be a steak or beef or whatever it is. And I may put the lettuce aside. Now, the idea is, regardless of how I separate the burger, I still end up with the burger. What I started out with is what I end up with. They may not be together, but it's the same thing. Even if I cut it up in small pieces, it's the same thing, but in different form. So based on the law of conservation, whatever I started out with, I must end with. And this is applicable to all chemical equations. The only difference is it may be in different form. So let's look at another concept here with the same burger, right? I know, I'm showing you this, I'm getting hungry as well. All right, but I apologize. I really apologize. But that's what it is, right? We just want to learn this concept really. And this is my best idea, I think, to show you. So I could break down this burger another way by giving you the buns or the bread. And I may also separate the meat. Maybe I don't like meat. And the lettuce. And so I separate it differently from the first concept. But the idea is what I started out with is what I end with. So that's all you need to think about. What you're starting with, what you end with. And so we're going to apply this to now our equations. I'm going to see how easy this is, right? As I'm saying, I want this to be really, really simple for you. And I hope I'm doing a good job at it, right? To make it simple, all right? Because I don't want you to be confused and I want to go confidently in exams and just answer any radioactive decay questions. All right, so look at this. The concept now that I want to apply to this is simple this. What I want to do is add the masses and the protons across the equations. Now remember now in the radioactive equations, the mass will be at the top. That's a typical way to write them, right? And the proton number will be at the bottom. The mass number is always larger, so look out for that. The proton number is always smaller. So let's say you have element X and has a mass number AB and the proton number CD. If you should decay this or break it down, you'll make it a particle Y or an atom Y with a mass number A and a proton number C. If you look at it carefully, we started with A, B. So where's the B and where's the D? So the next particle that is formed will contain the B and also the D. And of course, you want to identify what that new particle is. You look at the proton number. The proton number is what you use to identify the new element that is forming. Because the mass number can be different because sometimes you form what they call isotopes. And isotopes, even though the proton number may be the same, but the mass number may be different. So you can't use the mass number to identify the element. Okay, you want to go to your periodic table, look at the proton number, which is the same thing as the atomic number. So that's what I want to bear in mind, right? All right, so let's just run through this real quick. So the element that will be formed based on the atomic number D will be atom Z or element Z. All right, so let's move into some real numbers now. Let's say you have element X now. I'm moving from burger to letters, now to numbers. I'm getting it down, build up on the concept. So element X has a mass number 10, a proton number 5. All right. Let's say we decay that. And let's say we form particle Y with a mass number 4 and a proton number 2. Now let's do some mathematics with this, yes? So if you look carefully, you'll realize that from the 10 that you started out with, you get 4 as the first known particle. Then you want to now figure out what number can be added to 4 to give you 10. That is if you're only forming 2 products now, right? You can form more than 2 products, that depends. So always looking at what is formed or what is known. So of course, what we can do here now is add 6 because 6 plus 4 is 10, right? Remember adding the masses across the equation. So what can you do with 2 or add to 2 to get 5? Of course, that number is 3. And so we can call this now element Z, whatever element is, with a proton number of 3 and a mass number of 6. The idea is the masses must be equal, the proton numbers must be equal on both sides of the equation. That's just the concept I wanted to have. Once they're the same on both sides, you're pretty much good to go. So let's look at some specific example now. Let's look at the example here for radium. Now radium 226, right, with a proton number of 88, if it undergoes alpha decay or alpha emission, notice that emission said emitting the particles, giving off the particles. So if you give off the alpha particle, remember alpha particle is helium, again with a mass number of 4 and a proton number of 2. So what will happen here now? If you give off 4, so easy way to look at it, you can look at it both ways. You can look at what is required with 4 to give you 226, Or the easiest way you might want to say 226 minus 4. Why? Because it give off the 4. The arrow means it is given off. It is what is being produced. So 4 is being produced as a mass number. So the remaining atom will have the remaining mass. So 4 from 226 will give you 222. And now 88, you reduce it by 2 because you give off 2. Then what you should have here is 86. If you look in the periodic table for the atomic number 86, you'll realize this is radon. All right? And so that will be the new element or atom that is formed. Let's jump to one more example here. Let's say carbon 14. All right, undergo a beta particle, a beta decay, or beta emission. So in other words, it's lost a beta particle. And remember what a beta particle is like an electron. So you're going to give it off. You give off an electron. An electron has no mass and a negative proton because a negative charge. Now, follow the concept here quite carefully. If you should release zero mass, the mass number should not change, right? Because you're giving off zero mass. Nothing changes. But this is where the little trick is. You give off a negative charge, or consider it an electron, which is opposite of a positive proton. You lose a negative. A loss in electron is a gain in proton. So that's what I want to remember. A loss in electron is a gain in proton. Let's say that one more time. A loss in electron is a gain in proton. If you lose negative character, you gain positive character. Just remember that. So watch this now carefully. Let's do the maths though. Mathematically, again, if you minus 0 from 14, you get 14. If you should minus negative 1 from 6, because remember you lose negative 1, right? So let's do the maths now. You should get 7. How does this work out mathematically? It's simple this. 6 minus negative 1 equals 7. Yes? 2 negative give you a positive. Now again, you can even think about it this way. A negative 1 plus what number gives 6? It has to be 7. You can reduce 7 by 1, yeah? You reduce it by 1. So you reduce 7 by 1 to give you 6. Or you say 6 minus negative 1 gives 7. So whichever way is easiest for you. But the idea is both sides of the equation must be equal in terms of mass and also proton. So 0 plus 14 is 14. Negative 1 plus 7 is 6. All right. So I'm hoping this is getting really easy for you and getting more comfortable, right? All right, let's jump into our next example right here. Let's look at this example that we're going to look at here now is a gamma decay. All right. And I should have actually mentioned this to you right here. Again, remember, always look in your periodic table. Let's look at that quickly. Always look at the periodic table for your proton number and determine what element it is, regardless of the mass number, right? So nitrogen is the 7th element in the periodic table as atomic number of 7. So that definitely is nitrogen, right? So let's go to our gamma decay now. Now, a gamma decay, let's say iodine 125. And so if you notice I said gamma decay right here, think about the particle that's going to be removed and is an emission. You're going to remove no mass and no proton. But the question is now, how this makes sense? How this become a decay? How do we describe this type of reaction? Okay, let's not forget one little thing, right? I know that's a question that most students ask. What's the purpose of undergoing a gamma emission if there's no change in the atom? Actually, there is a change. Because let's remember the concept. What it started out with, it's unstable. Right? It's unstable. It is very reactive. And so when you lose a gamma particle, there's a loss in energy to make the atom become more stable. Think about if you do not have any food to eat, how much work can you do? You're inactive technically. You cannot do too much. The same thing with these atoms. If they lose a lot of energy, they cannot react readily because energy is being lost. So imagine the burger. You have no burger today, right? Hence, you're just going to feel really out of it. Because I know you're motivated by burgers. You just love burgers, right? So no burgers, no energy, you can't function. All right? So the same thing with these atoms. The loss of energy, they have less reactive power. All right? So that's the concept right there. Let's look at one last example here before we move on, right? Now, in this last example here that we're going to do, it said nitrogen 14. And remember, the number here that they list like this is always the mass number, right? So nitrogen 14 absorbed an alpha particle to produce oxygen 17. Now, the key word here is absorbed, right? Absorb is the key word. So remember that now. Look out for those words. Absorb the alpha particle. Not give it off, not emit it, but absorbed it. And another, it said oxygen 17 is formed on another atom. And it's asking you, what is the other atom that was formed? Now, don't stress over this. Let's take our time. Let's go through it. Let's write down what is given first. The first atom we're working here with is the nitrogen 14. So let's write that down. We know that nitrogen is the seventh atom, right? The atomic number is 7, or the number of proton is 7. They gave us the mass number, which is 14. It said it absorbed an alpha particle. Let's absorb mean to gain. So we're going to add the alpha particle now. Add the alpha particle, absorb it. Just remember that. So the alpha particle here, again, represents an helium. The mass number for the alpha is 4. The proton number is 2. That's been absorbed. The question also states that oxygen 17 is formed or is produced. So produce means it comes after the arrow. So oxygen 17, we know that if the mass number is 17, on the periodic table we're going to see 16, right? So of course you know this is an isotope, right? That's definitely an isotope. But oxygen, the proton number doesn't change from 8. It's always 8. If the proton number is not 8, it's not oxygen. So we can look at the periodic table and say, okay, once it's oxygen, the proton number must be 8. Now they're asking us now to find the other atom. How do we find that? Remember the concept. Total mass on the reactant side must equal the total mass on the product side. So if the total mass here is 14 plus 4, which is 18, then what will be the mass on this side? So let's think about it, yeah? We have 17 already. How much more do you want to become 18? Only one more, right? Let's look at the proton now. 7 protons plus 2 protons here, that's 9. On the product side, 8 plus what number gives 9? And there's only 1. What number should we use to determine the atom is the proton number. Here the number is 1. So what element has a proton number of 1? That's hydrogen. So the other atom that is formed here is hydrogen. Because remember the concept again, quickly. The masses on both sides are equal. The total proton on both sides are the same. And so from this we can conclude that the new atom there is hydrogen, right? So always look at the masses, the total masses, and always look at the total protons, right? So I truly hope this really worked out for you well today. And I hope you feel a bit motivated and a little bit more optimistic. Yeah, really do. So we're going to be at the end of it now, right? And definitely, without any doubt, I am totally appreciative of you stopping by, taking time to learn along with me, to get new concepts. And trust me, there are a lot of things that are going on in life, right? I just want to tell you, try your very best to be a part of the solution and a part of a problem. So do not be a part of a problem at all. I know sometimes it's hard, but you have to try. So hence be a part of a solution. That's what we're doing here today, all right? So be motivated. Be positive. At this time, peace out. Keep safe.